So optimization, so your goal of optimization is to optimize, either give me a maximum or a minimum of something, depending on what your goal is. The example here is a box. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. As shown in the figure, what dimensions will produce a box with the maximum volume? So they have a limited amount of material to build said box, right? But they want the maximum volume that they can have. So in your brains, you have to go back to these important words, surface area, volume, okay? And what does that mean? And they've given you some details, square base, that's important. And so you have to go back. They won't always give you a picture. In fact, rarely will you have a picture. So if you'd like to draw a picture, you can test your art skills as well. So if you look at the picture that they gave you, we have a square base, right? And so we do not know the dimensions of the base, but we do know is it's square, so it's x by x, okay? Because we're talking about a box, we also have a depth, we have a height here, We don't know that. You could do y, you could do h, it doesn't matter. So the first thing you're going to try to pick out here is what you're trying to optimize. So you are looking for the word maximum, minimum, right? And in this case, they tell you outright, they want to maximize the volume. So this is what would be called your primary equation. Your primary equation is the equation that you're trying to maximize. And you actually come back to it. So you figure it out and then you set it aside. So if my goal is to maximize volume, I need to figure out how to calculate the volume of this figure that they've given me. So volume is three-dimensional. For any prism, whether it be square like this in a box, or whether it be a triangular prism, whatever it is, it's the area of the base times the height. That is your formula for all volumes, right? It's your three dimensions, basically. Your two dimensions of your base and then your height. And so the square is easy. If I were to find the volume for this particular guy, I would say that the volume of this is going to be my base, x, times my height. That is my volume equation. So this would be my primary equation. So I'm going to find him and then I'm going to set him aside for right now. All right. My secondary equation is an equation that has more information. So they give me a limitation. If you were to think about it from Algebra 2, we call them constraints. All right, so you have a limitation on something in your secondary equation typically. And so the secondary equation here is the surface area. It says it has a surface area of 108 square inches. That's not variable. The surface area will be that many square inches, period. All right, so that would be our secondary equation, is surface area. And so we then have to figure out how then would I calculate the surface area of this guy. Well, surface area is the area of all the surface. That's pretty deep, right? And so the area of the base here, that would be x squared, right? And so that's part of my surface area. My surface area is going to be that x squared. I'm going to add to it the area of my sides here. And since it's a square, every side is going to be x by h. Everybody see that? Every side is x by h. And how many sides do I have? 4. 4x times h. Now, if I had a top, then I would have to consider that as well. I would have 2 of those x squareds. But I don't have a top, so I only have to worry about this particular one. I don't have to worry about adding the top in, all right? And so now my next goal is to then use the secondary equation to make the primary equation only have one variable. And so with the secondary equation, I'm going to say, well, not only is that my surface area equation, I actually know what my surface area is. It is 108. And so I want to solve that for one of my variables. Here's the kicker. If you have a variable that's squared, solve for the other guy. Or you have a square root, right? So I'm going to solve for h. So this is just a matter of manipulating your your equation like you would do for literal equations when you had literal equations back in Algebra 1, Algebra 2, or if you ever did it in chemistry or physics. You're solving for one of your variables. I'm solving for h. And so in order to solve for h, I need to subtract my x squared from both sides. I have 4xh equals 108 minus x squared. And then I'm going to divide both sides by the 4x. And I'm going to have h equals 108 minus x squared over 4x. And I will tell you, when you have something like this, it's probably easiest to divide it up. So to actually go ahead and say 108 over 4x minus x squared over 4x. And then you can simplify it by, I'm going to move this over so I have a little more room, actually reducing. And so 108 is going to reduce potentially, and x squared is going to reduce. But either way, you can, sometimes it works and sometimes it doesn't. You can plug either one in and it's going to simplify when you get there. All right, but if this is going to throw you off, go ahead and separate it if you want to. All right, it's up to you. So we have what h equals. Once you have what h equals, you're going to go back to your primary. So now we're ready to actually use our primary equation. All right, and so we're going to go back to this guy right here, and we're going to say my volume equals x squared times what my h was. Whichever one you used is fine. 108 minus x squared over 4x. All right, and so I'm going to simplify this first because I'm eventually going to take my derivative, all right? So I definitely don't want to take my derivative like this. I want to make this a little more simple. And so I'm going to do just basic algebra cancellation here. I'm going to cancel this x with that x, right? I'm going to distribute, and I am going to break it up once I do this. So if you had broken it up at first, that would be fine. I'm going to distribute that 108x over 4 minus x cubed over 4. And I'm actually going to simplify this guy too. So I get 27x minus x cubed over 4. And that is my volume, all right? And so all I've done is I've used my secondary equation to make my primary not have two variables, all right? And so then you want to think about the term maximum and minimum. Way back at the beginning of the chapter, how did we find max and min? Well, max and min always occur at your critical numbers, correct? Well, how do you find critical numbers? First derivative set equal to? 0. So if I am trying to maximize my volume here, I want to take the first derivative and set it equal to 0 because it's going to happen at one of those points. I might have to plug it back in and figure out which one, but it's going to happen at a critical number. That's the only thing that can happen. We've already proven that. So now that I have taken my primary and gotten it to one variable, I can now take the derivative. And so that's what I need to do. I am going to take this and I'm going to do first derivative. So first derivative of this guy right here. All right. What is the derivative of 27x?
27.
Right, so it's just 27. What about this guy here? X cubed over 4.
12x.
So multiply by 3. So it's 3 over 4, right? X squared. Right? Makes sense? 27 minus 3/4 x squared, or 3x squared over 4. However you write it, it's fine. I want to set that equal to 0. So set it equal to 0. How do I solve that? Subtract 27. I get negative 3/4 x squared equals negative 27. What do I do with that fraction? Multiply by the reciprocal times negative 4 over 3. I'm going to cancel here, right? Cancel my 3. Cancel that to 9. Negative 9 times negative 4 is what? 36. How do I finally solve for my x? X equals positive or negative 6. All right? So I know that my maximum is going to occur at either positive or negative 6. Now, I am talking about the dimensions of a box. One of these answers is not logical. Which answer is not logical? I'm not going to have a negative dimension, all right? And so if I'm talking about square inches here, I know that it has to happen at 6 inches, all right? It says what dimensions? Is 6 inches dimensions? When I have a cube, I need 3 dimensions, right? If I have a cube, that's the only way that it works, right? Or any type of box. So I know it's going to be 6 by 6 by something because I solved for X. How then do I solve for H?
Plug in 6 to H equation.
I have to actually plug it back into my secondary equation. It's the only one that will give me an answer to solve for. It's the only one that has an answer to begin with, right? My primary equation has no answer. It just is an equation, a function, right? So I have to go back to my secondary equation and plug in my 6. So I'm going to say 6 squared plus 4 times 6 times H should equal 108. Subtract your 36. So what, 74? Yes. Divide by 24. Please tell me it goes in evenly. Or did they not give me one that goes in evenly? No, they didn't. They're not very nice. No, it did. It says 3.
Is that 74?
It's not 74. It's 72. H equals 3. There we go. I was like 74 doesn't go in evenly. 3. So my dimensions are going to be 6 inches by 6 inches by 3 inches. There would have been so many options for this box to have 108 square inches. I mean, if you just give 12 people 108 square inches of material and you tell them to build a box, the chances of them building the same exact box are slim to none, right? Because they can just build it. What you do see is the 6 by 6 by 3 volume is 108 compared to the other volumes. And so it's interesting to me when I see something and you're comparing, like you've probably seen this before where they're like, which holds more, right? And visually you're thinking this one would, but the other one does. And so just visually you wouldn't think that this guy is the guy that would maximize that volume visually, but he does. And there's only one answer. It's not like you could come up with 2 different answers for optimization. There is one answer, unless for some reason 2 dimensions give you the same volume, which can happen. But then you'll get 2 different answers. You will get those same 2 answers and say, hey, these 2 answers give you the maximum volume. But very often one of your critical numbers will logically cancel itself out like it did in this particular problem. On the bottom of page 212, it gives you your guidelines. Identify the given quantities and quantities to be determined. So figure out what you know and what you don't know. When feasible, make a sketch. You're not being judged on your artistic skills, but it does give you a picture in your brain. Write a primary equation for the quantity that is to be maximized. So when you see the word maximize or minimize or whatever, you should immediately know that's your primary equation. And you notice that little hint there. A review of several useful formulas for geometry is presented inside the front cover. So inside your front cover, you have some integration rules and you have this little guy right here that gives you some geometry. If you flip the page, hopefully, there we go. You have all these little geometry guys here.
The SAT booklet gives me geometry I never use.
Right, it does. Reduce the primary equation, have one single independent variable. So you're going to use your secondary equation to get your primary equation to one variable. Determine the feasible domain. So that means that there are answers that will make sense and answers that will not make sense. -6 for a dimension does not make sense. All right, so we just eliminated that completely. And determining it by calculating your techniques. So if you have more than one critical number, you actually have to plug it in and see which one gives you your max or min. Because one can be a max and one can be a min. And so you might have to determine that by plugging it back into your equation, just like we did when we did first derivative and plugged it back in to our equation. All right? All right. Let's see. Oh, he's a fun one. We'll do him. Go to, example 3. Good times, giving us fractions here. Yay. They zero out, so that's nice. All right, so this one says rectangular pages to contain 24 square inches of print. The margins at the top And bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. So you can see they have a figure here. If you did not have a figure, you would want to draw something like that. Think about the logic. Top and bottom margin, 1.5. There we go. Left and right margin, 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Least amount of paper. So they are wanting us to minimize the size of the paper. All right. And so that's what we're going to do. We are going to look at the area of the paper itself, and then we're going to use our secondary equation to help solve it. So what they've done is they've done an X and Y for the print size. All right, the print size. Square inches, the word square tells you it's 2 dimensions, so you know that you're finding area there. And then they've drawn out the margins. So if I were going to do a primary equation here, I am minimizing the area of the paper. All right, so the formula for the area of this paper is going to be my width. What is my width? Y plus 2 times my length or height. Yeah, x plus 3. So that is my primary equation. I am trying to minimize that guy right there. All right, my secondary equation then is going to be the print area. The print area is just what? What is that area? Just x times y, and we know that's going to be exactly what? 24. In this case, it does not matter which one I solve for because I have one x and I have one y. They're both going to be a fraction because I'm going to divide 24 by either x or y. In your book, they solve for y, which is fine. So if I solve for y here, I get y equals 24 over x. All right? And so I'm going to take that and I'm going to plug it into my equation. And instead of y, I'm going to write 24 over x plus 2 and x plus 3. You could do your product rule if you want to. I would actually FOIL this thing. I would FOIL it and not use a product rule because, yeah, who wants to do that? So 24 over x times x is just 24 plus 72 over x plus 2x plus 6. So you're going to get 30 plus 2. Did they combine those two or no? No, they didn't. Okay. Plus 2x plus 72 over x. Yeah, it's probably easier not to get a common denominator. All right, that is my area. And so I can just take the derivative of that. It looks menacing, but it's not. So if I take that derivative, my 30 goes away, right? It's just a constant. This becomes just 2. This is 72x to the negative 1, right? And so it just becomes negative 72x to the negative 2, x squared. And I think they probably just, I would actually write it like this. That, all right. And then solve for 0. Subtract your 2. Again, it looks more menacing than it is. We have negative 72 over x squared equals negative 2. When what you're trying to solve for is on bottom, you can flip both sides. So you can reciprocate both. So this is the same thing as negative x squared over 72 equals negative 1/2. All right. Multiply both sides by that negative 72. X squared equals 36. They did it to us again. Our positive and negative 6. One of these is not a good dimension, negative 6, right? So we just found x. X equals 6. If x equals 6, you plug it into this guy. So y equals what? 4. 4 by 6. So since they are asking for the area of the page, or the dimensions rather of the page, then you need to add in those given margins if they want the dimensions of the actual page itself. We found the dimensions then of the print area, 6 by 4. So we would just take the 6 and we would add the 3 to it from this. We would take the 4 and we would add the 2 to it from that. And we would get that the dimensions of the page itself are 9 by 6 inches. Pause the video here and try this problem.